Okay, so thank you, everybody, to have joined us in this final keynote session. And first of all, let me welcome all of you, Andrew, David, and we are still missing Hashem, but he's going to join us. And obviously, all of you that have been joining us for the conference. So thank you very much for being here today and for this fantastic keynote session on the econometric modeling of climate change and the COVID-19 pandemic. So I've been thinking about how it would have been best to introduce our keynote speakers today. On the one hand, I could have taken 10 minutes each to list their fundamental contributions to econometric theory, to econometric methodology, to empirical econometric analysis, about the understanding of macroeconomic phenomena, and also about climate change and the COVID-19 pandemic. But we all know about this, as we have been citing them 50,000 times so far, because we all have been and still are their students in a way or another. Among us, some lucky ones were able to learn from them directly, following their classes, and spread around the world, there are thousands of these lucky ones. The number of unlucky ones largely dominates, though. Spread around the world, there are thousands and thousands of people who have learned from them through all their 324 articles, 672 papers, 16 books, hundreds of presentations at conferences, seminars, and keynote lectures. So I decided to do a different thing today. I have decided to take this occasion to thank you, Andrew, David, and Hashem, for all what you have done for our profession, for all what you have taught and keep teaching to us during your cumulative 150 years of activity, for having been and being a source of true inspiration to all of us. So thank you very much for all this and for being here today. And I think we can move to the first keynote lecture for today. And the first keynote lecture is David. Is on forecasting climate change, pandemics, and economics. And David, the floor is all yours.
Many thanks indeed for that very generous introduction, Claudio. It's a pleasure to be here. Is that showing correctly?
Yes.
Yes, thank you. Right, so the key issue is climate change, evolving pandemics, and economic shifts. It's the change, the shifts, and the evolution that pose the problems. If the world were stationary, it would all be dead easy to forecast, but it's extremely non-stationary, so it's very difficult to forecast. So we can see this along the top in these panels. There's very little atmosphere on Earth. There's even less water on Earth, believe it or not, and the climate is therefore causing big changes in temperature and in different parts of the globe. So I'll give an introduction to what's going on, then we'll look at forecasting changing climate, evolving pandemic, shifting economic relations, and then very briefly comment on forecasting scenarios, policy, and draw some conclusions. So climate change affects pandemics, we know that, which badly impact on economic activities we've seen dramatically in the last couple of years, which in turn is a source of climate change. So they're highly interacting. They're, however, measured at vastly different data frequencies. Paleoclimate at 1,000-year intervals, climate at annual, monthly to daily, economic data monthly, quarterly, and annual, and pandemic down to daily, and in finance, even seconds and nanoseconds. So there are different frequencies across different disciplines. Nevertheless, there are very powerful commonalities across all three. They're all subject to non-stationarities, both from evolving stochastic trends and sudden distributional shifts, location shifts. They're subject to data revisions and even changes in data measurement systems. All three face imperfect and incomplete knowledge of their data generation processes from human behavior, which keeps changing. So they have to search for reasonable approximations. And all three need forecasts of likely future outcomes to plan and adapt as events unfold, albeit over very different horizons. So how would you make forecasts in these three disciplines? Well, first of all, let's look at the common components of all forecasts. They all have unobservable stochastic errors, unknown values for the forecast origin. They've observed stochastic variables, income, prices, etc. And they've deterministic terms, trends, seasonals, constants, and dummies. Each component can have one of three mistakes. It can be estimation uncertainty about where the economy is. The model can be misspecified by omitting key variables, and parameters can change. So we can set up a taxonomy table of 9 interacting issues. If we let B denote a biased forecast and V a forecast error variance, and we put the components in columns and the problems in rows, then unobserved terms, for example, estimating the forecast origin, if you get that wrong, you'll have biased forecasts. And even if you get it right, it'll be uncertain for a period and you'll get variance components, as you certainly will from stochastic errors. Misspecification, omitted variables, they actually, given this taxonomy, would only cause variance effects because all their bias effects would be picked up by the deterministic terms. And then there's change. For example, the innovation error variance can shift, the forecast origin can be more or less badly estimated depending on developments in nowcasting. Stochastic variables parameters need estimated, and that adds variance. They can be misspecified, and that adds variance. And they can change, and that adds variance. And again, remember, these are all conditional on the other components being absent. So here, change in parameters of stochastic variables, if they've got a non-zero mean, will be picked up by the deterministic terms. Estimating these as a variance effect, misspecifying them as both a bias and a variance, and change has a variance effect. Now, many of these categories include lots of things. For example, mismeasured in-sample data is included in unobserved misspecification, unmodeled nonlinearity, and incorrect exogeneity. But if you had an accurate forecast origin and we removed all in-sample location shifts, forecast period change would be the only bias factor remaining. So this term here would be the only B. That would go from accuracy, and that one would go from no misspecification. So when 3C, this deterministic terms change, forecast failure will result. And this has happened across all three disciplines. If we look at the change in atmospheric CO2 over ice ages, these variations of plus or minus 25 parts per million over 800,000 years match the coming and going of 8 major ice ages. And recently, it shot up by more than 100 parts per million, a complete explosion that would have been unpredictable, say, in 1600. Nobody would have the faintest idea that was going to happen. Likewise, new confirmed cases has sudden accelerations, sudden falls. In Britain, we get negative values because of idiocies and recording data and then losing it. And that changes regularly. And of course, back from May onwards, it's going back up again. The lockdowns have had huge impacts on the UK's economy. Annual changes in hours worked, annual changes in real GDP have dropped very dramatically, the biggest falls in several hundred years, dwarfing what was called the Great Recession. And of course, the UK never had the Great Depression, so this is massively the largest it's ever seen. And trend changes are happening all the time. If you look at the trends in, say, UK productivity, I've done it in logs, they're shifting all over the place and recently have both stagnated and then collapsed with the pandemic. Now, we all work with structural or theory-based formulations, particularly in climate, but also in epidemiology and economics. And these formulations are important to help us understand what's happening in our discipline, but almost always they have indifferent to poor forecasting records. And the key forecasting problem is that the models, structural as they're called, ignore location shifts. And because they're equilibrium correction mechanisms, most models of observational data turn out to be that, they'll converge back to their inbuilt equilibria, even if that is no longer the relevant location after a distributional shift. And the result is they'll be mispredicting quite systematically. And we'll see some classic examples of that shortly. Now, one of the problems is a lot of econometrics and statistics textbooks don't point out something that's known by almost everybody, that Euclidean geometry is only valid in a plane. Conditional expectations are unbiased and minimum variance only if distributions do not shift. And if they do shift, they're neither unbiased nor minimum variance, nor is the law of iterated expectations valid. But you've just seen that these are happening all the time. So these are not sensible ways to set up forecasting models, structural models like DSGE, which are completely non-structural. Every time we get a major shift in distribution, then the law of expectation, the law of iterated expectations fails, and what happens in the next period will not be what the model expects. Now, there are two solutions to systematic forecast failure after shifts. You could adapt to theory-based systems, and that's certainly something I've worked on for many years, or you could use robust statistical predictors. Andrew will talk about the kind he's using in the next session. But handling location shifts in all three disciplines' models of observational time series improves their forecasts, suggesting there's quite a lot of generality in some forecasting methods. So some generally helpful forecasting practices that have evolved in my group over the years, and this work is all jointly with Jenny Castle and Jürgen Durnig, is to dampen estimated trends or growth rates in the forecasting period. Average across forecasts from non-poisonous methods. Model averaging is a well-known procedure, but often they still include what we call poisonous methods that forecast very badly, so the average doesn't help you as much as it should. You should always include forecasts from robust devices in that average. Select the conditioning variables in a forecasting model at a very loose significance, 10 to 15%, not the usual 1 to 5%. Update estimates as data arrive, especially once you've seen forecast failure from either parameter or linearity changes, and shrink estimates of autoregressive parameters in small samples, which is something we did in our relatively successful M4 competition entry. But other practices are also helpful. Adapt the predictor choice to the data frequency and to whether it's scalar or multivariate. You need to address special features like seasonality. This has badly affected a lot of the forecasting methods out there who haven't realized that there's considerable seasonality, not in the behavior of the pandemic, but in the recording of the pandemic numbers. You need to retain theory models as the null when selecting over other candidate variables. We suggest applying saturation estimators for in-sample outliers and shifts. And then if you are amongst the groups that difference data before forecasting, check that it's not going off course very badly by accumulating to see what the levels forecasts look like. So using these as the background, let's look at what we do in forecasting climate change relationships. So here's a graph of the changes in atmospheric CO2 since 1960, with three trend lines drawn in, rising quite rapidly, leveling off, and then accelerating away. Now, of course, we hope to bring this under control. Paris is in here, but it hasn't helped in the slightest to bring CO2 emissions back under control. And the net result is that global mean surface temperature deviations are changing hugely. Trend line here, and a steeper trend line there. So is ocean heat content deviations down to 700 meters and on down to 2000. Again, the trend lines are changing over time. And if you look at the global sea level rise, it's accelerating, now rising to about 0.14 of an inch per annum against 0.05 of an inch over the whole period 1850 to 1992. So change, change, change. If we look at the distributional shifts in monthly global atmospheric CO2 from the late 70s to the late 50s to the early 70s, it's there. If we go ahead to the 1980s, it shifts to there. If we go on to the start of this century, it shifts there. And then, despite Paris, it shifted way out into right field with numbers that are huge compared to anything in the paleoclimate record, as you saw in one of the previous graphs. Now, climate examples usually based on coupled model in comparison projects, now CMIP6, which play a major role in climate analyses. But from the viewpoint of an econometrician, these are conditional ensemble-based scenarios rather than forecasts, because they separately require forecasts of CO2 values, which of course are very difficult to forecast beyond the immediate future, and they therefore often use representative climate pathways as the basis for their analysis. Now, in our work, we've used vector autoregressions for the UK in its CO2 emissions, particularly after its 2008 Climate Change Act, which is a major policy intervention, since gone from 80% reduction by 2050 to net zero greenhouse gas emissions by 2050, without any idea how they will get there. We've used a simultaneous equation system, something that isn't so popular these days, when modeling atmospheric CO2, Antarctic ice volume and temperature over the last 800,000 years of ice ages, driven by Earth orbital variations, as laid down long back by Milankovitch. The orbital variations are calculable far into the future, so we can actually forecast 100,000 years ahead, assuming that the relationships between the variables are not altered. They won't be altered relative to the orbitals, but they might be altered within themselves, particularly the atmospheric CO2. And we can compare such outcomes to those if anthropogenic greenhouse gases continue at the present rates. So what's the UK done? These are UK CO2 emissions in tons per capita per annum, rising very dramatically from 1860 up until the end of the First World War, oscillating violently in the interwar period, peaking in 1975 and crashing since. There are many reasons for this behavior. One of the most important is the behavior of coal, the minor strikes causing some of these massive variations, the great increase over that period, and then the substitution of oil for coal, leading to a fall in coal, and then the substitution of gas for oil, leading to a fall in oil after the oil crisis, and then the rise in renewables. These are all in megatons of oil equivalent. There's also the huge increase in the efficiency with which power, electricity in particular, is used. The ratio of CO2 emissions to capital stock in the UK has fallen by 92% since 1860, as it has in the US, although the US record on CO2 emissions in tons per capita is not very good. It started off kind of where India is today, rose way above the UK at the roaring 1920s, crashed in its Great Depression, peaked at about 22 tons per person per annum, and is still well above 15 and needing to be brought under control, as clearly President Biden is attempting to do. So does it pay you to model in-sample shifts or just to use small samples? Well, if you don't model in-sample shifts in 2008, which is this drop here after the Climate Change Act, the forecasts are very poor. Going from 2012 to 2017, they have a root mean forecast error of 94, whereas if you actually model the breaks, you get a root mean squared forecast error of 29. And I'll come back to this method. This is a scalar method rather than a vector autoregression. We call it CARD-T. And it's pretty accurate, and certainly much more accurate based on just a few observations here than building a VAR back to the beginning of this century. The ice ages are the next major target, because since we can go very far into the future, we can see what would happen if we didn't deal with climate change. So here the data are measured at 1,000-year intervals in the x-axis from minus 800,000 years ago up to the present, which is 0. And we have super strong exogenous orbital variables. Nothing we do about our climate will affect the Earth's eccentricity, which is determined by the gravitational pulls of other planets, the obliquity, which is its leaning back and forth, and its precession, which is which part of the climate faces the sun in summer or winter. We model that with data up to 100,000 years ago, forecast the remainder to test the system, which is fine, then forecast 100,000 years into the future. Partly, it's just fantastic for a poor macroeconomist to be able to forecast 100,000 years ahead under any circumstances. So the orbital drivers have been two very big cycles over the last 800,000 years. the smaller cycles in between. Quite a quiescent period here, and we're in a fairly quiescent period now. But they're definitely not stationary, but there's certainly no sign of a unit root. This is a circular orbit, and this is a deviation of about 5% from circularity into an elliptical orbit. If you look at obliquity, it has changed in variance over time and come back a bit into the future. Precession has also altered. You can see big white gaps here, and then you can see big red ones overlapping here. And it's often converted into summertime installation, but we use the original driving variables. What's happened because of them is that here I've plotted the negative of ice volume in order to have it positively correlated with everything. This is it positively correlated with CO2. And you can see there are quite big departures at the beginning, which might be measurement errors, but also at other points. They're not perfectly correlated in any shape or form, because these are many thousands of years. Likewise, CO2 and temperature have varied quite a bit, and temperature and the negative of ice have varied a bit less than all the others. And this is a three-dimensional plot, ice volume increasing here, CO2 emissions here, temperature here, and you can see there's a lot of nonlinearity built in to the 3D plot. The last ice age started ending 25,000 years ago, and Rudiman argues that humanity was actually influencing the climate from 10,000 years ago by domesticating animals and starting farming. But more recently, a long paper by Snurn, his co-authors, suggests that in fact, humanity started affecting the climate 23,000 years ago, well before Neolithic farming, because they found protoweeds dating back that far, and they need ground disturbance to grow in new areas. And they found quite a lot, and protoweeds being something that become weeds in due course. Now, the Earth's orbital path is known far into the future, so we can calculate scenarios for atmospheric CO2 with no human intervention, continued anthropogenic emissions at roughly where we are, 400 parts per million, and 560 parts per million, roughly, RCP 8.5. And we start forecasts 10,000 years ago because of Rudiman's argument, but you could start it 23,000 years ago. So if humanity was not affecting CO2, and these red lines, which are the data, suggest it is actually doing so, but we've started where it wasn't affecting it, we'd get cycles very like ice age cycles in the past for both ice volume and temperature. But we have been affecting it, and in fact, the forecasts lie exactly along the data from 10,000 years ago towards the next one. And these are showing that at 400 parts per million, we'd have much less ice. These are the confidence bands, and a much warmer Earth. But if we move to 560 parts per million, we get a very explosive reduction, almost an ice-free planet, and a very much hotter one, which of course is what drives it to be ice-free. So it's not a great idea to continue it. Business as usual, ending up at RCP 8.5. Now, a small side effect that I've often noticed but hasn't seemed to be picked up in the forecasting literature is that what happens in sample and what happens in the forecast period can be quite different, even with a common model. So if we look at a var with 4 lags and we take the standard errors in each equation, that's got no orbitals, and we keep the same model and add in the orbitals, the standard errors of fit are very similar. It's a bit lower, it's a bit higher, it's very similar. But when you look at the root mean squared forecast errors, this is virtually a third of that. This is 30% less, and this is almost 50% less. So the fact that something isn't helping you much in sample doesn't mean to say you shouldn't check to see how much it would help you out of sample, which is something Graham Meisen and I analyzed almost a decade ago. So evolving pandemic impacts, would you use different models? Well, we have used very different models because it's at a very different frequency. They're very short term. We're forecasting enormous numbers of countries, states, local authorities, 4 models for each time we do it. So that's 3,200 model estimates every time. It's about 4 times a week, so that's 12,000. And we've ended up forecasting a week ahead. So everything's got to be automated. You can't do this by human intervention. And that's all in Jürgen's COVID-19 website. So these are the cumulative confirmed cases. Total deaths, as you can see, the trends have moved all over the place. These are new confirmed cases and new deaths, and these are weekly vaccinations and the accumulation of vaccinations, which again has been increasing up till about May. That many in the public now look at forecasting methodologies because epidemiological susceptible exposed infectious removed models made enormously high predictions about the number of people who would die if we didn't do anything. There are also many statistical predictors involved: autoregressions, theta methods, CARD, Andrews growth curves. And the problem is there's a non-stationary pandemic process, which you saw oscillating around. There's continually changing trends, explosive routes in some periods and abrupt shifts. And these are salient features of the process. However it's observed, they are ongoing. Location shifts and policy interventions, lockdowns have a major effect. Evolving technological advances like far better tests and vaccines, and rapidly changing trends as behavior and virus infectivity changes. So every aspect of UK cases and death distributions have altered since the start of the pandemic a year and a half ago. But the non-stationarity of the pandemic process interacts with the non-stationarity of the measurement process. As there's major measurement errors that suddenly get corrected, there have been very big definition and testing changes, including care homes in the UK. There's been lags in data releases at weekends, which have generated weekly changing seasonality. So it matters enormously whether you're forecasting on a Sunday or forecasting on a Wednesday. From Sundays, you'll see forecasts are way below what happens, and Wednesdays are way above, because the data have all been pushed from one to the other. They're changing measurements, testing for infection and antibodies has hugely increased. Data errors, we had this farce of losing 16,000 cases because of a wrong kind of spreadsheet that led to some negative cases, and suddenly the data are corrected and you get very large revisions. So we'll focus on real-time short-term forecasts of confirmed cases and deaths using our method CARD-T, which I will now briefly describe. So these are our local authority forecasts for England. This is in 9th July last year. This exactly a year ago, not too bad. Then it explodes because of an idiot government that says, oh, you can have a free Christmas, go and do what you like. And so it spreads like wildfire. And this is what's happening on the 3rd of July, our forecast for a week ahead. As you can see, some areas are very bad. And funnily enough, these are exactly the areas where disease was prevalent in the 18th and 19th centuries. So it's meant that distributions have been shifting all over the place, really dramatically, sometimes spreading out hugely, sometimes looking very concentrating compared to what happens later. So CARD-T decomposes the data into a trend, a seasonal, and an irregular component. And then it forecasts these components separately and then aggregates them. So trend and irregular, we use a calibrated average of rho, delta, and thema, C-A-R-D-T. Rho estimates a simple autoregressive model with seasonality. Delta estimates growth rates based on first differences, but damped and aligned for seasonality. And thema is an arbitrary trend halving with an intercept correction based on a moving average model. And the seasonal components just extrapolated from most recent estimates of the seasonal pattern. Then we compute the arithmetic average of these three forecasts. Then it's calibrated by treating those forecasts as if they were observed. We fit a richer autoregressed model to the extended data series, a bit like X12. And then the fitted values from this calibrated model are the final forecasts, undoing any transformations such as logs and differencing, which is roughly what we entered in the M4 competition. So what happens? How do we do it? Well, here's a short period, and all of the estimates are based in very short periods because of the considerable non-stationarity. So the current trend is estimated by taking moving windows of data, saturating every moving window with a linear trend, so there's many trends as observations, and then we select the relevant ones using Econometrics. Then these selected linear trends are averaged to give an overall flexible trend, which, as you can see, describes the existing trend pretty well. Then the trend and regular separately forecast using CARD, damping the trend for forecasting, and the seasonals extrapolated and added to the forecast for the trend in the regular, and then we compute uncertainty. But then we also go back 3, 2, and 1 day in this case, and we also apply the same method and produce forecasts from them. These get averaged, and the reason for that is when the black line, which is based on data from 3 days earlier, lies below the red line, you know that cases are accelerating. And if it lies above, you know cases are coming under control. So let's look at Italy, which was the first country to really major changes. This is forecasting Italian total deaths on 6th of March. The red line's way above the black, but it's hugely affected by this sudden acceleration in deaths, which our forecasts are well below. But 1 day later, it picks that up because of the change, and off it goes. And now it's going all the way through, but it's dramatically lower than the black line's dramatically lower than the red line. So you know it's accelerating way beyond anything previously observed. So we've done forecast comparisons, both to LANL, the Los Alamos National Laboratory, which is forecast published twice a week since April 2020, and IHME, which is still forecasting. How well do we do against LANL? These are confirmed cases, these are deaths, these are horizons up to 7 days ahead. As you can see, we're pretty much the same for confirmed cases, but we're very much better initially for deaths, very much lower. By 7 days ahead, we're back in line. If we look at the interval forecasts, which we regard as equally important, they're definitely very close to 10%, much of the time with a few big outliers, whereas we're significantly below. So we've got confidence intervals that for some reason are too wide, and we haven't quite worked out why they're too wide at this stage. But that's better than being too narrow and overconfident. If we compare to IHME, the Institute for Health Metrics and Evaluation, it's quite difficult because on the 12th of August, they changed the definition of a death as being on the death certificate to being only counted if it was within 28 days of infection. And this led to a big drop where the old data stay up here and the new data come down here. We immediately moved to forecasting the new data, but IHME have stayed forecasting the old data for quite a period. So it's very hard to know how we compare. And then the third category is forecasting shifting economic relationships. Now, most economic forecasting models are equilibrium correction. And after shifts, to avoid systematic forecast failure, because they're converging back to the wrong equilibrium after a location shift, you have to use robust methods. You have to correct that the EQCM is no longer the right one. And here's a classic example, which is really, in some sense, quite astonishing. This is UK productivity, and that's the previous trend. And this very simple model of forecasting the level by an intercept, a trend, and the lagged feedback worked extremely well up until roughly 2007. And after that, productivity stagnates. And what are the OBR forecasts? They continue forecasting, trying to get back to the trend. And look at the length of time, 2008, forecasting up to 2022, completely wrongly and way off. What they needed to do was to adjust the intercept to a local mean, and then adjust the equilibrium correction to be around that local mean, and produce smooth, robust forecasts. And the root mean squared forecast error drops from 3.63 to 0.87, and you can see the massive improvement. So you've got to avoid what we call the hedgehog effect, which we see regularly in economic forecasts of trying to get back to the old equilibrium when it's no longer the correct value. There's also been a slight paradox in Britain of stagnant real wages, which I see when I'm a macroeconomist, as shown in this graph, and rising real incomes, which I see when I'm a climate economist and I'm looking at GDP per capita. So these real wages and log output per worker are relative to employment, whereas log wages have fallen, the share of wages in GDP has fallen quite a lot. In a number of countries, this has happened. But in Britain, log employment has risen very much faster than log population. So a lot of the paradox disappears in that if you divide GDP by population, it's very much higher and growing than if you divide it by GDP per employee, where it's definitely stagnated. But last week, the Office of National Statistics said, oh, we got all the measurements wrong. We did single deflations. We deflated output prices and input prices for the same deflator, but actually they're quite different. So now if you deflate them by their own deflator, you get definitely growth in productivity, not dramatic, but it's not completely stagnant. So beware, you make a forecast, data suddenly get revised and a long way back. So productivity is not quite so stagnant now. Right. Forecasting in all three disciplines are made from both statistical and there are two types of structural models, with or without including policy variables. The forecasts from all nine, the three disciplines and the three types of models, tend to entail a need for policy reaction. For example, the climate ones reduce greenhouse gas emissions. The pandemic ones develop a vaccine. The economic ones improve productivity without in any way saying how you do it. So the structural models in climatology and epidemiology rarely link directly to specific policies, such as invest in renewable electricity generation, subsidize vaccine research, create innovation hubs, etc. Integrated assessment models try to link climate and economics, and some generalizations of SEIR link pandemics and economics, but the IAMs would need to forecast technological progress to evaluate how good renewable solutions will be. Almost all macroeconometric models are built to link to policy very explicitly, for example, to interest rates, so that central banks can say, oh, we'll raise interest rates and bring inflation under control. But unless they've handled past shifts, be careful using their advice. Climate change scenarios or forecasts, as they're often called, are conditional on greenhouse gas emissions. And the implied policy is indeed the need to rapidly attain genuine net zero emissions, not fake by having offsets, etc. And that has indirect implications for achieving it through BCCS, CCS, renewables, etc. Multi-period unconditional forecasts would require forecasting future emissions, but in turn, those are dependent on policy choices, although the sea level rise is already baked in, so are highly predictable. The integrated strategies to reach net zero greenhouse gas emissions by 2050 have to address a giant range of issues. The huge expansion of highly variable renewables only electricity, its storage, transportation, buildings, manufacture, chemicals, tackling agriculture and waste. And there are several papers out there, Rebecca Wolf, and our submission to the UK House of Commons Public Accounts Committee, which proposed how you might be able to deal with most of these without actually getting precisely to net zero. In pandemic control policies, the forecasts of pandemic evolutions through epidemiological and statistical models rarely have direct implications of how best to control. And the effectiveness of medical and non-pharmaceutical inventions depends on their availability, and they differ over the course of the pandemic. So we're now relying, because of our silly government, just on vaccines and not anymore on NPIs. But the policies can be linked, as Andrew has done in other work. There are various agent-based models also studying the impacts of NPIs and other models linking them to economic outcomes, as Hashem has worked on quite recently. Forecasts from SEIRs often effectively really scenario warnings to make NPIs for no vaccines available. So the initial one said, oh, 500,000 deaths, you've got to do something. So the policy reaction was instantly to lock down. Of course, the policy reactions then mean you don't get 500,000 deaths. So they invalidate that scenario, but this is not forecast failure. You have to distinguish from when the policy reaction invalidates the model and when it just invalidates the forecast, because that's exactly what you wanted it to do. Now, forecasting in policy and economics, very rarely have people used robust predictors after shifts because they don't have policy relevance. A random walk may be your best forecast without policy content, but if the random walk forecast is very different from the econometric model forecast, perhaps you ought to think again as to whether you should use the econometric model forecast, you might still use it for policy. So this is the UK monthly unemployment rate, and you can see this upturn here. But given the lockdowns, that upturn is very small compared to what you might have expected. So we've compared the 3 months ahead forecast from card T, an econometric model with and an econometric model without a furlough policy intervention dummy. So these are the levels of unemployment up to March 2020. And then we've got April, May, June, July, and August. Now the scenario that we're looking at, so to speak, is the econometric model says, ooh, unemployment will rise dramatically. But the government introduced a furlough to pay 80% of salaries. And consequently, the actual outturn is nothing like what the scenario would have said, but you could say the scenario told the government, you better have a furlough policy or unemployment will rocket. Now the forecasts with the furlough are very poor when you've only got one observation to estimate it from, but when you've got 2 observations, it's actually quite close to the outturn. Card T is very close to the outturn initially, but after the abolition or withdrawal, if you like, of the furlough, it starts to go wrong and be seriously under. And indeed, this is one of the basic problems in forecasting. If you are forecasting April, card T is massively the best, and the other 2 are identical because there's no furlough effect. That's still true in May. By June, the furlough model is doing a lot better. By July, it's actually doing better than card T. And by August, the original model is back doing better than either card T or the furlough dummy model. So which model works best is shifting much of the time, and that's true in general in economics. So in January 2020, the Bank of England forecast the unemployment rate would be 3.8% for Q1, and we forecast 3.9. But in August, the bank predicts 7.5 in Q4, whereas we predicted 4.7 with an outturn of 5.1. So you've got to be careful if you're using econometric models to forecast and not looking at what the forecast would be from a robust predictor. Right, some conclusions. There are clear commonalities across climate, pandemic, and economic observational time series. All 3 face major non-stationarities from stochastic trends and abrupt shifts, so they do need robust forecasts to plan over different horizons. All 3 have incomplete knowledge of their data generation processes, which entails model search for structural representations. Excuse me. There are major forecasting similarities and differences across disciplines, though, partly dependent on the accuracy of the data, its frequency, partly in the availability of valid conditioning variables, and partly in the extent of non-stationarity. I've tried to illustrate this by applications and compared forecasts in all 3 areas. So thank you for listening.